Hi everyone. Thanks for coming along today. I should just start off by introducing myself. I'm a data engineer at Yelp, and I'm based in London. This is now my 5th country this month, so I'm kind of exploring whole new forms of jet lag that I didn't realize existed anymore. So hopefully this will still come out in a vaguely coherent way, but please excuse me if I trip up on any of the details. So my talk's about smart join algorithms for fighting skew at scale. Though I'm part of the machine learning group at Yelp, it's not really a machine learning talk. It's really about how to counter some specific problems with the shape of your data that can cause Spark to kind of trip over itself sometimes. So I'm going to start off by talking a little bit about exactly what we mean by skewed data, what kinds of skew can appear in data sets, and how to detect when Spark's having a problem caused by skew. Then the rest of the talk is going to focus specifically on joins, because that's something that, that's an area where Spark has particular problems if the data is very skewed. So I'm going to dive into how they work and why this is problematic. I'm going to talk about some tricks you can do to join skewed data more efficiently. So this can let you speed up joins sometimes, or sometimes it can even make something that would never have succeeded in any reasonable amount of time actually possible. And I'm going to round up by talking about a few kind of further extensions to the same theme. Riff on the idea a bit for however much time we have left at the end. Hopefully there'll be time for a couple of questions, but if not, just grab me on the way out and we can chat. So what do we mean when we talk about data skew? Well, like your classic statistical definition of skew is basically when you've got an asymmetrical distribution which is heavier on one side than on the other. Or another way of putting it is if the mean of the data is very different from the median of the data, that's a sign that your data is skewed one way or the other. But we're interested in probably more of a sort of less formal, slightly more pragmatic definition of skew, because there are lots of different kinds of phenomena in your data which can cause joins and other operations in Spark to get messed up. They could also include when you've got specific sets of outliers that might appear to the very end, like at one end or the other of your distribution. Or even like in a similar way, you might actually have a multimodal distribution where you've got two different distinct subpopulations in your data or two different processes, and whatever variable you're interested in is very different between those two groups. So if you plot the distribution of the data, you might see something like this with separate peaks. But there's one area that I'm going to dwell on a little bit because it does crop up a lot when you're working with data from the web, which I suspect a lot of people here probably are. And it's something that I've seen over the course of my career in a bunch of different companies, not just Yelp. So this is a kind of distribution called a power law, and that just means when one variable is proportional to a power of another variable, you know, like y equals x squared or something like that. What these manifest as in practice is you get a very small number of individuals with a very high value for that variable, and many on the long tail with a very low value for that variable. And a true power law, if you plot it on a log-log scale, it will come out as a straight line. So where do these appear? Well, a lot of natural processes all across different sciences seem to follow power law distributions. In many cases, they're actually approximations, but for the purposes of this talk, that doesn't really matter. Like quite often there'll be a power law for most of their range, and then at the ends they do something slightly different or whatever. So for example, the force of gravity, the inverse square law, is a power law. The clue is in the square in the name. Distribution of earthquake magnitudes follows a power law. So you get a very, very small number of extremely powerful earthquakes. I mean, hopefully the San Francisco's next one isn't going to happen while the conference is on. And then you get a very long tail of very, very weak earthquakes that you wouldn't even notice. Distribution of income, Pareto's law, that's also a power law. And there are examples from life sciences as well. For example, there's a relationship between the body size of an animal and its metabolic rate, called Kleber's law. But maybe more relevant to this kind of audience, they also crop up a lot in data that comes from human behavior, human choice, human preferences, that kind of thing. So if you're working with, say, natural language data or recommender systems, your data, you'll often have data sets that are power law distributed. They're kind of important to know about from a data science point of view because they make certain analytical tasks a bit tricky. Like they don't really have a well-defined mean. What is the mean of a curve that looks like the thing on the left? Well, it's probably like just over 0. What does that really tell you? Not a lot. But they're also important from an engineering point of view because they make a lot of engineering tasks harder. But yeah, they'll pop up in lots of places. So for example, the curve I just showed was a distribution of word frequencies in a natural language corpus. So the most frequent word, which in English is the, appears many, 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 many times. And then there's a very rapid reduction in frequency. You know, it's obviously followed by things like of and a and, but then eventually you get to the long tail of words that in any given corpus only appear once, and then all the rest of the words in your dictionary in any given corpus probably appear 0 times. Degree distribution in social networks is another place where you see this kind of stuff a lot. So Twitter used to talk about the Justin Bieber problem. I imagine it's somebody different now. I'm not really sure who the most popular person on Twitter is these days. But they had to jump through a lot of engineering hoops because, you know, if you're sharding by user ID, then as soon as Justin Bieber does something, then that causes a problem for whichever machines are processing his part of the Twitter sphere. Participation on things like wikis and forum sites, any other places where you get user-generated content, that tends to follow power law distributions with a few kind of like elite power users doing most of the work and the vast majority of users not contributing at all or maybe even just once throughout their entire lifetime there. And in fact, the popularity of websites in general across the web or content on a lot of websites also follows power laws. There's lots of academic studies about this kind of thing, so it's important to be aware of these things because of the problems that they can cause when you're building applications to process that data. Okay, so we get it, Andy. So some things are much more popular than everything else. Some people are much more popular than everything else. Why does that cause a problem? Well, it kind of depends what you're doing with that data, right? So I kind of touched on this a moment ago talking about Justin Bieber. If you're sharding by a particular key and that key follows a power law distribution, then you're going to get hot shards in your database. Certain machines will be hugely underperforming because they're doing the vast majority of the work. For actual online web services, you know, serving pages or serving content for pages, you can end up with, for example, slow load times for certain users. Like I remember from a previous job, like some users had reported that their shopping basket page would always crash. Right? It turned out that they were using their shopping baskets as bookmarks instead. They would just add loads of things to their baskets that they never intended to buy instead of using the actual favorite facility. And somewhere I think there was some algorithm in the back end that was doing something that was n squared and you didn't notice it for most users, but suddenly you get some outliers like them, and the whole thing just takes longer to render than you've budgeted for, and you get timeouts and crashes, that kind of thing. But you're probably all more interested in data processing tasks, right? So, I mean, for map-only tasks, these kind of skewed distributions aren't really so problematic because, I mean, if your data is already distributed by a key that's got an unfriendly distribution like this, you can just randomly reshuffle before you apply the map to each of those rows, right? But the problem comes when you're doing joins or aggregations, because generally then you have to direct all of the data for a given key to the same node in your cluster, the same executor in Spark terminology. And that poses a problem when some of those keys are hugely overrepresented. I'm not really going to talk about aggregations, because that could be a whole separate talk. But I'm going to dive into why this causes problems for joins and what you can do about it if you see this occurring. So first of all, before we get to that, how can you tell it's a problem? Well, it usually manifests itself as, for a given stage in your job DAG that's performing some kind of reduction task, most of the executors will finish, most of the tasks will complete, and you'll get a handful or sometimes even just one that is running and running and running, and you just don't know when it's going to stop. Or sometimes some task will run to completion, and you're going to figure out why it's taken a while, and then maybe you look at the statistics for that stage in the Spark UI, and you notice like a huge difference between, the numbers in the 75th percentile column. These are measured in megabytes, but these are like 2 orders of magnitude more, right? The time, this is measured in seconds, and this is nearly an hour, for example. So then you can dig in and see, if the completion times of the different tasks follows that kind of pattern. If most of them are finishing really quickly, one or two or a handful are taking a really long time, then you might have a data distribution problem. There's an associated cost problem with that, right? Because while all of the other executors are just sitting idle waiting for that stage to finish, you're basically wasting money, right? Because somebody else could be using those nodes for a different job. So why do we get this kind of performance hit from skewed data? Well, let's dig a bit into how Spark joins work under the hood, and that will become a little bit clearer. So your standard kind of join in Spark is called a shuffled hash join. So on the left here, we've got a data frame which is large. On the right, we've got another one which is smaller, just for the sake of explanation. And they're color-coded according to the key. So all of the rows on the left-hand side that are red all have the same key, and the row on the right-hand side, which is red, all has that key. So in order to perform the join, Spark shuffles both sides so that all of the rows that have the same key from both sides end up being partitioned together. Because then if you're going to output a new row that contains like the columns from the left and the columns from the right, you've got to know that you've got that data. Each executor has to have that data local to it in order to generate that output row. I'm glossing over a lot of the details here, but they're not too important. Hopefully this gives you an idea. So you might have certain tasks that are processing data for more than one key. That's fine. Like the top one here is processing like the dark gray and the light blue keys. It all depends on basically how those keys are hashed into, I guess, a task ID. I'm probably getting the terminology a little bit wrong. But the important point is you can't have one key split over several executors. So they all have to be partitioned together after the shuffle, co-located after the shuttle. And that's usually okay, but then what happens if you've got very skewed data? So obviously that means then, because you've got to send all of the data for, like in this case, the dark gray key to the same node, that node is going to sit there and sit there and sit there, working and working and working, long after the other ones have finished. But we don't really have a way to take advantage of Spark's parallelism because we can't split that workload over several nodes. One way around this is with a broadcast join, and that avoids doing a shuffle altogether. So that lets you load one of the data frames into memory. It broadcasts it around the cluster, loads it into memory on every executor, and then those executors can process the join in place with whatever data they've got because they know they've got all of the data from the other side. So in this case, data frame 2 is being broadcast. We don't have to do any kind of shuffle, so from that point on, it becomes a map-only task. But the problem is that data frame 2 has to fit in memory on every executor. Also, you sometimes get reliability problems when you're broadcasting an awful lot of data around your network at once. That's something I've noticed in the past. I've ended up turning the auto-broadcast feature off so that I can control when I'm doing it and when I'm not doing it, because sometimes I've had jobs fail because Spark's being a bit over-optimistic about what it can broadcast. So this is only a solution when you've got small data on one side, smallish. So how can we do this faster? Actually, I should say joining skewed data faster / more reliably there, because part of it is sometimes enabling a join that would otherwise fail. What we really want to do is to split the workload for a single key across multiple tasks, so we still get the benefit of parallelism. By the way, don't feel like you have to take a picture of every screenshot of every slide, because there's going to be code examples and things. I'm going to post a link to the slides on Twitter this afternoon, and my Twitter handle's on the last slide, so that might be easier. No problem. So effectively, you pick a replication factor, and that's basically a knob that you can tune by trial and error. And for the skewed data, you randomly append the replication, a number between 0 and that replication factor to the existing key that you want to join on. So you make a composite key, basically, of original key plus a random number in that range. So that basically splits up the skewed data into these buckets, they're sometimes referred to as. And then for the non-skewed data, you replicate that side, so data frame 2 in our example, the one on the right-hand side, you actually replicate that data r times. So there's one row for each bucket ID in the range between 0 and the replication factor. And again, you generate a composite key with the original key and the replication ID. So the way that works visually is all of the rows with a replica ID or bucket ID of 0 go into one partition. Sorry, all of the rows for each key that have a replica ID of 0 go into one partition. All the rows for each key that have a replica ID of 1 go into a different partition, and so on. So you're not replicating the data from the skewed side, data frame 1 on the left, you're just splitting it up into these buckets. And then each bucket gets a copy of the entire data frame from the right. And then you proceed with the join as normal on the composite key that you've generated. I'll show some code in a sec, which will explain that better if you prefer thinking in code. So it's doing something a little similar to a broadcast join, as in one of the data sets is getting copied around, but it's not memory bound. So you're not limited by having to have a copy of it in memory on each executor. Overall, your cluster's doing more work, but the limiting factor really here is the time taken for the longest task to finish, and this should bring that down, even if some of the other tasks are doing more work as a result. So the interesting thing about these is you can implement them at the application level. You don't need to kind of dive into Spark internals and write custom partitioner or something like that. You can actually do this even in SQL, or in this case, in the data frame API. So you generate a range, which is just a table containing the numbers from 0 up to, say, 0 to, what do we choose, 10, so it'd be 0 to 9. And then you cross-join that with the uniform data that you want to replicate, and then you create this composite key. I mean, you could just do it by joining on two fields, right? But here, to make it a bit more explicit what we're doing, I'm generating a composite key, which would look like the original ID, and then a separator, and then the replica ID. So you've got 10 copies of each row in that side. And then for your skewed data, well, for a start, we need a function to generate a random integer, which, bizarrely, I don't think Spark has one built in. But then we randomly generate an integer in that range for each row from the skewed side. And then we proceed the same way. We generate a composite key, which has got the original ID and a separator, and then that random integer. So that defines which of these kind of like logical buckets each part of the data goes to. And then that's it. Then you can just join them together on that newly generated composite key and drop that key afterwards because you don't need it anymore. But there's a caveat there. It only works for inner and left outer joins. So assuming your skewed data is on the left-hand side like it was in these diagrams. And the reason for that is, if you think about it, if you try to do a right join after generating those composite keys, you'd break the semantics of a right join because, for example, say you've got a replication factor of 3, there'll be one partition which has got a replica from the replicated side, but there is no equivalent row from the non-replicated side that's got that replica ID because there only were 2 rows with that key on the left-hand side. So then you'd end up with this row coming out, and that shouldn't happen in a right join. You should only get a row that's null on the left if there was no input data on the left for that key. So yeah, be careful. Make sure you only do it when it semantically makes sense. So inner joins or left outer with the skewed data on the left. So just to kind of validate this and prove it works, I did some experiments with synthetic data. I generated 100 million rows of uniformly distributed keys and 100 billion rows of data with the keys drawn from a ZIF distribution. That's the same distribution that governs the word frequencies in natural language. Because, you know, if you're going to test it, you might as well test it at scale. And a regular old inner join ran for more than 7 hours. This was on a pretty beefy cluster, I think maybe 200 cores. Most of the tasks had completed long before that, and I think it was just maybe 2 or 3 left, and there was no way for me to tell when they were going to stop. So I killed it eventually. And then I tried it using this replicated method with a replication factor of 10, and it completed in an hour and a quarter. So that's good. Can we do any better than that? Oh, there are some things you can do if you really need to tune it a little bit more. So you might say, well, it's only really the keys that are very common on the skewed side that need to be subdivided, right? All of those ones in the long tail that might only occur a handful of times or once, that's fine. So you can do something I call differential replication. I don't know if there's an established term for it in the databases literature or whatever, but effectively, if you can pre-identify which are the very frequent keys, you can use a different replication policy for those than you do for the rest of them. And you can do that in Spark relatively efficiently because of this freak items operation. And that actually uses an approximate data structure. I don't remember what it's called, but it lets you scan through some data in ON time and pick out the keys that appear very, very frequently above some threshold of, so in this case, the ones that account for more than 0.0001 of the rows. Because it's an approximate data, it's an approximate algorithm, you can get false positives in there, but not false negatives, so that doesn't really matter. So maybe you'll be over-replicating some, but that's fine. So then what you do is you have a different replication factor So in this case, say 50 for the keys that appear a lot, and 10 for the ones that don't appear very often. That could even be 1 if you didn't want to replicate those at all. So first you use this freak items call to actually gather the IDs that you want to treat differently. And then, sorry, I skipped a bit. And then you generate a replica ID range for separately for the high replication and low replication subsets of the data. So between 0 and 49 here for the high ones, and 0 and 9 for the rest. So then, for the data that is in that top set of very frequent keys, you on the uniform side, you then replicate that many, many times. You'll notice that I'm kind of doing a join here, and you're like, well, wait a minute, isn't this, we've done another join, isn't that problematic? But actually, you're only joining onto this list of very frequent IDs. You don't care about the rest of the data. Plus, you can broadcast that anyway, so that's really quick. So that replicates the rows from the uniform side that need to be replicated a lot of times. And then for the rest of them, the ones that don't appear in this frequent items list, you do the same, but you only replicate them according to replication factor low, replication low, so in this case, 10 times. Then you union these back together. So you've got this table that's got all of the replicas for the uniform data. Some of them have been replicated a lot, some of them have been replicated a little. Visually, it's kind of like this. So we take this, we get the skewed data, we do a freak items call on it to gather the frequently occurring keys. In this visual example, it's only the dark gray one. Then we broadcast join that out and then replicate the non-skewed data a number of times, depending on whether they occur in that set or not. So, this is kind of replica set 0 has got the dark gray key and all of the others. Let's say we've got 3 replicas here, and we haven't replicated any of the other data because, just for the sake of making the diagram easier, I've assumed like we're only replicating the frequent ones. I hope that's clear. It probably makes more sense if you work through the code. So then for the skewed data, you kind of do the same as you did before. You generate a random number to make the composite key for each row. And again, you have to draw that from the range for the high number of replicas or the range from the low number of replicas, depending on whether the ID is in the frequent or the rare set. And then at the end, you just join them back together, exactly the same. You can drop the composite key afterwards. So I went back to my synthetic data set, which, as you remember, completed in about an hour and a quarter using the fixed replication factor. And then I tried that with a differential replication strategy, so 50 times replication for the very, very frequent keys and 10 times for the rest of them. And it finished in under an hour, so I guess a speed up of, I guess it was maybe a bit more than 20%, which isn't huge, but this is all kind of icing on the cake, like if you really need to tune a job. The important fact really is that by using replication to start with, we can get the job to finish, even when it didn't finish before. So just before we wrap up, there's a few other kind of related ideas that are worth talking about. One is this idea of partial broadcasting. I think the book High Performance Spark has got a tutorial on how to do this. So this works in a slightly different way. You also start by identifying the very common keys from the skewed side. And then you split the uniform data into 2, depending on whether their keys are in the very frequent set or the rest. And then you do a broadcast join for the subset of that data where they are in the frequent keys set, and you do a regular shuffle join for the rest of them. And then you union the two resulting joined data frames at the end. So yeah, this is, I think, like, intuitively to me, this seems like a better way of dealing with, like, when you've got a few specific outliers that are very, very frequent. So you filter them out and treat them in a completely different way, rather than maybe kind of a sliding scale like you would get with a power law, for example. There's also, you could also say, well, look, if you've got that kind of sliding scale of popularity behavior, can't we maybe replicate each key a different number of times depending on how frequently it occurs, instead of having a single strategy or like a head versus tail cutoff? And in fact, this is what the Scalding library for Hadoop does. So if you're not familiar with Scalding, it's a Scala DSL, like functional DSL for writing map-reduce jobs that was developed by Twitter. It's kind of fallen out of use a bit now because everyone uses Spark for this kind of thing, but they have quite similar APIs. And I think maybe because of Twitter's Justin Bieber problem, Scalding comes with these kind of skew join techniques built in. It's where I got a lot of the ideas for doing it in Spark. They do actually have a method for doing exactly what I described. So getting an approximate frequency for every key in your skewed data set, and then with some parameters that you can tune along the way, dynamically replicating the data from the unskewed side, depending on how frequently each key appears in the skewed side. Because you've got often a sliding scale between the very common and the much rarer ones. I couldn't actually make this work in Spark. I don't know if there are any kind of join geeks out there who've tried it themselves. I suspect it might have been down to a difference in how joins are actually implemented between Scalding and Spark, but there's probably no time to go into the details of that now. But like, in theory, it's a great idea. In practice, like, your mileage may vary. You can also extend this idea to cope with skew on both sides, and this is something else that Scalding does. So it's a bit hard to follow from all the blurb on the slide, but the idea is you have two different replication factors, one for each side, because you might have more or less extreme skew on both sides. So you generate for each row you replicate each row according to how frequently it appears in the other side, and you generate a random ID for it for this side, and vice versa. And then you have this composite key which has got the original key, the replica ID for this side, and the replica ID for that side, and you join on all three of those. In practice, though, that doesn't actually happen that often, because usually what you'll find is you're joining between some source of data that's very skewed, like logs, and some source of data like a snapshot of a database table from your production database, which isn't skewed. One time that this can come up is if you're doing some distributed matrix operations or graph operations, and you've got maybe a users versus items graph, and you've got some very, very overactive users and some very overpopular items. So you can find that this might be useful in those situations. But yeah, if you want to see how that works, I'd recommend digging into the Scalding source code, because it's reasonably readable. Okay, so just to sum up, there's a few things that you could think of before you even get as far as trying one of these techniques. So first of all, if the problem is genuinely just outliers, then maybe you're better off just dropping them from your data completely. Like, for example, if you're building a machine learning model, and this is all to generate training data for it, if you've got like items which are ridiculously overpopular for the wrong reasons, like they've gone viral because they look stupid or something like that, or you've got like users which are actually bots or something like that, then actually keeping those in your training data is not going to really help your model, because you're trying to make better predictions for the real users, and the majority of items which aren't like popular for the wrong reasons. So think about your actual use case. Maybe you can just use like freak items to pick out those very, very top outliers and just drop them completely. But maybe you need them in there, like maybe your use case is bot detection. So you need to keep all the data from bots and not throw it away. If you can do a broadcast join, that's the easiest thing to start with because that's literally just like one extra function call in PySpark and it will do the rest for you. But then if that doesn't work, then look into your data, see if it really does follow some kind of pattern of skew, like a power law, exponential distribution, something like that. And then if you're going to go down the route of using one of these more complex algorithms to make the join possible, then I'd say start simple with a fixed replication factor, and then make it work, and then if necessary, iterate to try and make it run faster. So I just want to give a shout out to a few places where a lot of these ideas came from. There's the book High Performance Spark that I just mentioned. There's a blog post that I found which does the fixed replication strategy in the RDD API. And I more or less just adapted those examples to work on data frames for this presentation. And like I said, I got a lot of the ideas as well from the way Scalding handles these things. Plus a big shout out finally to the data engineering community at Yelp who gave me a lot of feedback on this. And of course, we're always hiring, check the website, same as everybody else. So yeah, like I said, I'll post a link to the slides on Twitter in a bit. So if you do want to see the code, then you can grab it off there. Thanks very much.
I think we have time for one question if somebody has one.
Hey, thank you for the talk. This was very interesting. I was wondering, do you know if there are any plans to integrate this with Catalyst and CBO, where you have histograms on your join keys, so to do this automatically?
I don't know, but that seems like maybe that might be what they had in mind when they built histograms on join keys. I mean, I think this is how some commercial distributed databases do it. But I'm not really a Spark committer or Spark contributor, so yeah, fingers crossed they might be doing that.
Hey, thanks for the talk. I have a question. So when we replicate the data 10 times, are we physically replicating it, or is some kind of logical replication?
No, you literally physically replicate it. So because you generate a table containing the range between 0 and 9, and then you cross-join that to the original data, and then you're then shuffling by the composite key. So the 9 rows that don't have a match on the other side, they'll disappear into a black hole once they've reached the other end of that shuffle, if that makes sense.
All right, cool. Thank you.
Sorry, you might want to grab a mic if there's a question. Okay.
One simple question. Have you ever experimented with custom partitioners, for example, to control filling of partitions or something else, maybe in data frame?
Stochastic partitioners, did you say? I didn't quite hear the question.
I mean, have you ever experimented with a custom partitioner? For example, you own partitioner, not hash partitioner, or etc.
No, not personally. Like, we do most of our Spark work in Python, and
okay.
So yeah, I think that makes it quite hard.
Excuse me. Here.
I think we probably
we're actually out of time for questions, but
sorry,
I'm sure you can catch up with the speaker at lunch or outside the hall. Lunch is now served down in the expo hall, and the talks will resume at 13:40. Thank you.
Thanks.